AP Calculus, Unit 7, Day 60. Our objective is to find general and particular solutions for differential equations. So, solving differential equations. We're looking at examples of variable separable differential equations. Given below are differential equations with given initial condition values. Find the particular solution for each differential equation. So we're finding the equation of which the differential equation is the derivative. So we're starting with the answer and we're working backwards to go through, and this is we're undoing the derivative to get back to the function. And just a differentiable equation is just a derivative. We know that as y prime, we know that as f prime of x. For this stuff, we're going to focus on dy dx. Okay? And going back to the first part, general and particular solutions, think of this as if I took the integral of x dx with no intervals, so that's the indefinite integral, we found that to be x squared plus 2. X squared over 2 plus c. That's what I meant to say, so let's write this down. So if I knew I was looking for the integral of x dx, we would say, hey, I'm going to raise that 1, x squared over 2 plus c. Okay, that's a general solution. Right? So now, if I do the integral of x dx, what I'm now saying from 1 to 3, so now it's x squared over 2, and I'm going to use the fundamental theorem of calculus from 1 to 3, and I'm going to get a particular solution. So the same thing will come to light if we're given a point. We can find the specific solution. If not, we'll find the general solution. So this would be 9 halves minus 1 half, which is 4. So very specific. Okay, so kind of in the same way as we're talking about general and particular solutions. All right, so what do we do here? Separate variables. So as I go through, first of all, I have dy dx. Just like when we were solving, a over b equals 13, and the problem said solve for a, I know I'd multiply both sides by b, and I'd get a equals 13b. Okay, so we've been doing that for a long time. So now I can multiply both sides by dx. So I get dy equals 6x squared plus 6x plus 2. And now we have the dx over here. So I have all my y's. There were no y's in this part of the derivative. Because again, this is the derivative. We're trying to find what original function gives me this. And so there's all my y's. They can be understood as 1. There's all my x's. Well, now what I'm going to do is I'm going to take the integral. And notice I'm taking the integral over here with respect to y. So the integral of 1 is just y. And now normally it'd be y plus c. We're not going to write the c right there. And now on this side, we take the integral of this polynomial. So take each one separately. So this is undoing the power rule. So we add 1, 6x cubed over 3, plus 6x squared over 2, plus 2, I'll write it all out, 2x 1 over 1, plus c. Now, I could have written plus c over here, plus c over here. Well, there's constant on each side. Bring it over. It'd still be a constant. I want the constant over here. So let's just simplify this. So we're now going to get y equals 2x cubed plus 3x squared plus 2x plus c. Okay, so this is my general solution. Okay, so every function that looks kind of like this is the general solution to this derivative. If I take the derivative, 3 times 2 is 6, 6x squared. 2 times 3 is 6, subtract 1, 6x. Derivative of 2x is 2. Okay, doesn't matter what the constant is. But they give us this information. This is 1 point. Okay, and this goes back to what we were talking about when we first started doing derivatives. It didn't matter what my, let's say I have parabola, whether I have x squared, whether I have x squared plus 8. Again, these are all can be y equals, f of x equals, or I could have x squared minus 5. It didn't matter. they all look like that. But all of them have the same derivative. Okay, so that's really what we're doing. We just said, hey, that's a general solution. Now let's find when one point is on that graph, I can know the exact function. Okay, that's what's known as the particular solution. Okay, so let's look at how we do that. Well, -1, when x is -1, y is 2. Well, let's put that in there, and then my only unknown is the constant. So now, on that point, only one of these functions will go through. So every place I see a y, I'm going to put in a 2. Every place I see an x, I'm going to put in -1. And now we're going to solve for c. Okay, so we just substitute -1 and 2 for y, and do some simplifying. We get c equals 3, and then we just put that into our general solution. And we put 3 in for c. There's our particular solution. Okay, let's go through the second one. I have all the work done out. So again, we want to separate the variables. All the x's are already over here, but I got to get the dx over. So we multiply both sides by dx. I also got rid of the radical. Wrote that to the 1/2. So now let's take, first of all, excuse me, let's take this x to the 1/2, bring it up, make it x to the -1/2. We're going to distribute that in the next step. And the divided by 2 becomes 1/2. So we're going to take the integral of both sides. Okay, so now the integral of dy is just 1y to the first, 1y to the 1. Add 1 to the exponent. So this is nothing new. We just becomes x to the 1/2, and then divided by 1/2, which is multiplying by 2. Those are going to eventually cancel out. 6x squared divided by 2. So hey, the 1/2 and the 2 cancel out. So that's just x to the 1/2, which is square root of x. 6 divided by 2 is 3. We add the c. Notice you can add the c to both sides. You may have a professor that'll have you add c to both sides. So this is our general solution. Look at the original problem. The point was 0, 2. So I replace c and x. I put in 0. That makes it nice and easy. 0 plus 0 plus c. And then equals 2. C equals 2. Place that in. There's our particular solution. Okay, I'll do number 3 for you, and I'll give you 4 to practice. Okay, so this is the first one where I do have a y on both sides, and I have x's on both sides. So I'm going to multiply. It's kind of like our we have a proportion, so means extremes, cross product property. So I multiply both sides by 2y, and I get 2 by dy. Multiply both sides by dx. I get x squared plus 2x dx. Okay. And now I'm going to take the integral of both sides. Integral of 2y is 2y squared divided by 2, which will end up being y squared. Integral of x squared is x cubed over 3. Integral of 2x squared is 2x squared over 2. And I'm just going to write the constant on this side again. You can write the constant on both sides and then bring it over. That's fine as well. Right, so let's simplify, and I already started to simplify here. So this is going to be y squared. Y squared equals 1/3 x cubed plus x squared plus c. So now, and again, we're looking for the particular solution here, so I'm going to put in 0, 2. If I had to do the general solution, I take the square root of both sides, but we're just going to, right now, we can still solve for c, given our point right here. So every place that I see at 1, I'm going to put in 2. Every place I see an x, I'm going to put in 0. Again, that makes it nice for us. Okay, now let's solve this for c. Okay, so we get 4 equals c. Now I'm going to have to go back, and now I do have to solve for y because I do want my particular solution. So I have y squared equals 1/3 x cubed plus x squared, but now it's plus 4. No problem. So I'm going to take the square root of both sides. Hopefully remember that whenever I take the square root of both sides, then I need to have a plus or minus. So y equals plus or minus the square root of 1/3 x squared plus 4. But one of of the things I have to pay attention to was that I was given that 0.02 is on the graph. So when I go through and let's check both of them. You don't have to write these out. You can just kind of do them in your head. But I got to check plus the square root, and then I got to check minus the square root. And whatever I put in for x should come out to be 2. So when I put in 0, what do we get? 0, 0, 4. So that's going to be positive 2. That's great. And then when I put in 0 in the other one, so this equals positive 2. When it's the negative square root, that equals negative 2. That doesn't work. So my particular solution is going to be, and I always like to write it in function notation, so it's going to be f of x equals plus, you don't need to write the plus, square root of 1/3 x squared, x cubed. Let's try that again. X cubed plus x squared plus 4. And that is our particular solution for this differential equation. Okay, but you do have to pay attention to the positive and negative signs. All right, let me just go through, try problem 4 right now on your own, and then we'll go through it. Okay, so here we go. Same thing, multiply both sides. So we get y dy equals x plus 2 dx. Let's take the integral of both sides. So we get y squared over 2 equals x squared over 2 plus 2x plus c. Remember the constant, again, professor you have next year might make you do the plus c on both sides, then bring it over. But we can just do it on the right side. Now let's put in what we know. And again, I don't need to solve it now because we have a point. So having this point will allow me to go through and find the particular solution. So every place here y, I'm putting in negative 3. Every place here 1, we're putting in, actually every place here x, we're putting in 1. Okay, find out that c is 2. So now there's my c. I start this by eliminating the fraction that I had. So we divide those by multiplying everything by 2. So now I have y squared equals x squared plus 4x plus 4. Take the square root of both sides. I probably should put plus minus up there. And once again, I got to check. And I knew my original point was x was 1 and y was negative 3. So when I put when I put 1 in, that's 1 plus 4 plus 4 is 9. And when I take the square root of 9, that's 3. And only the negative value would work. So that's my particular solution. Okay, so these aren't that bad. It's separating the variables, just like using proportions, just like we did in algebra 1, putting all of one variable on one side and the other variable to the other side, and then just taking the integral. Okay, in the next part, we'll look at a few problems, a little more advanced,